In this lesson, I'll show you how to solve a linear system by Gauss-Jordan elimination. The question reads, solve the following system using Gauss-Jordan elimination. As you can see, we have a system of 3 equations and 3 unknowns, x, y, and z. And if you watched one of our previous videos where we used Gaussian elimination with back substitution, it was the exact same system of equations. And the difference between Gauss-Jordan elimination and that with back substitution is nearly identical. In fact, what you do is once you have your matrix in row echelon form where you have ones along the main diagonal, you then try to make the numbers above the ones in the second and third column zeros. So since this is an extension of what we did in the previous video, we ended off with the following matrix. Notice that this matrix has ones along the diagonal, and at this point you can easily solve for x, y, and z through back substitution, although we don't want to do that here. Now, in case you're confused about this, make sure you watch the previous video about Gaussian elimination and back substitution. And the steps are also outlined to your left in case you want to do this systematically on your own. Now, as mentioned, one of the differences between this method and the previous is we want to make this number into a 0, this into a 0, and that into a 0, because by doing that, we can easily find out what x, y, and z are. And unlike before where we used this one to make all the numbers underneath 0, this time we'll use this one to make these two numbers 0, and then subsequently use this one to make that 0. That being said, let's start by trying to get rid of this negative 2 over 3. And we can do that by multiplying all of row 3 by 2 over 3, and then adding it to row 2. Then we replace row 2 with the answers. So I'll multiply row 3 by 2 over 3, and I'll document that. Row 3 gets multiplied by a factor of 2 over 3, and then we add to row 2. This will replace row 2. Multiplying these two by 2 over 3 doesn't change it. This makes it 2 over 3, and over here we end up with 2. Now we will add 2 over 3 to negative 2 over 3. That makes this 0, and adding 2 to 0 makes this 2. So our brand new matrix should look like this, where row 1 and row 3 are unchanged. Now that I have my matrix, my next step is to get rid of this 2. And I can do that by multiplying row 3 by a factor of 2 and subtracting it from row 1. Let me go ahead and document that. Multiply row 3 by a factor of 2 and then subtracting it from row 1. Now if I do that, if I multiply this by 2, that becomes 0. This becomes a 2, and this temporarily becomes a 6. Subtracting 0 from 1, I get negative 1. That's a problem, and we'll get rid of that negative 1 soon. 0 minus minus 1 is positive 1. 2 minus 2 is 0. And 6 minus 9 is negative 3. As you can see, I got rid of the 2 and 6 so we don't get confused. And as I mentioned, we don't want this to be negative 1, so I'll multiply all of row 1 by a factor of negative 1. And if I do that, this becomes positive 1, which is what we want. This becomes negative 1. That remains as 0, and this becomes positive 3. So our new matrix should be 1, negative 1, 0, and positive 3, and the other two remain the way they are. Our last step is to get rid of this negative 1. We can easily do that by adding row 2 to row 1. So row 2 plus row 1. 0 plus 1 is 1. 1 plus negative 1 is 0. So this becomes a 0. That remains as 0. And 2 plus 3 is 5. So our matrix is 1, 0, 0, and 5. Remember, this represents x. 0, 1, 0, and 2, this represents y, and 0, 0, 1, and 3, this represents z. So we have z is equal to 3, y is equal to 2, and x is equal to 5. And that is exactly what we found when we did Gaussian elimination with back substitution. Let me write that down. 5, 2, and 3 is our solution. And there you have it. That is how to solve a linear system by Gauss-Jordan elimination.